Greetings everyone. I am Vishwajit Sarnabat from team B0110. As outlined, our proposed solution of federated deep reinforcement learning for smart traffic management system, I am going to demonstrate it in action. First of all, we are going to use the map of Berlin, specifically this region. The reason is that because OpenStreetMap offers the pre-configured controllable traffic signals for this region. Though with some efforts, it could be done for the Indian region too, but for now, we will go with this map, which is already available. Next, what we are exactly going to do is that first I will run the simulations in SUMO using the fixed traffic light signals, and then we will compare its performance on our own trained model, which has been trained for about 500 epochs to be exact, and then we will compare its performance heads on. So let's go on. First, we will run it for the fixed traffic signal. Here, what it basically does is that it will run the simulations in the default Sumo mode, which is just like how traffic signals work traditionally or how they work now. So yeah, you can see the changing of the colors is taking turn by turn here, which is how it works in the traditional fixed time traffic control signal. So far, it's working good in this region. It's good here. Now see here, the traffic jam has started forming here, slowly and steadily. That's an inefficiency there. Here too, we can see that. And because of the effect, it has now started piling up here too, continuously. And it just keeps on increasing. Yeah, now it's now actual jam. Let's see how other regions are doing. We can see that even there is here is an inefficiency. Even though there are a few vehicles entering from this side, the vehicles here have to wait. Even though the density is high, they are not being freed, which is like injustice to this region. Now see the traffic has been started piling up wildly here. It was started here. We saw that. It took a around turn, affected this region too, affected this region too. Now the entire city seems blocked. Yeah, the entire city is blocked. Now you can see at the time it took about 40 seconds for the simulation and the entire city is under the traffic jam. About 42 seconds for now. So let us close the simulation. Now we will run the same simulation, the same environment, and the same density or number of the vehicles entering and exiting the environment. But just we will use our own train model for 500 epochs and let us see how it performs. Okay, so run the simulations. We will check every junction here properly. You can notice that it is not a fixed control signal. I can see the hopping between these two, which is not in the fixed traffic signal where they take turn, not just based on the priority basis. Everything looks clean, very smooth traffic flow overall the city. Is the traffic piling up? No, it has been freed here. You can remember that this traffic started piling up here in the last simulation, which led to the entire city's traffic jam overall, like a domino effect. But so far, it's working so good with our model. Let time go. Mm, Smooth. You can also see is there here the inefficiency or the bottleneck here has reduced. In the last one, the vehicles were piling up until here or even more before they are being freed. But now, see, yeah, okay. So far, so good here. Yeah, let us see here. I can see the traffic piling up, but not too much. It is being freed up, no traffic jam until now. And we can remember that the entire city has started jamming until now. It's about 38 seconds, 39 seconds. And yeah, the entire traffic has been freed in about 39 seconds. And we can remember that we ran the previous simulation for about 42 seconds, which jammed the entire city. So yeah, it proves the effectiveness of our solution.